Hello, welcome back. For the first class, we introduce the dimensional analysis, and then we summarize the independent pi groups and the independent pi groups. For independent pi groups, we have four pi groups. The first one is the Reynolds number, second is the Maher numbers and the Weber, and the final is the four numbers. So Reynolds numbers is for the viscous effect, and the Maher number is for the compressibility effect, and the Webb number is some effect related to the surface tension force. So usually we will meet these problems at the liquid to gas interface problems. And the four numbers is related to the gravity force. And for the dynamic uh, similitude problems, we know that if we let the independent pi groups are equals, that means uh, the independent dependent pi groups also equal to. So this is very important if we meet some problems and we would like to take the prototype behaviors by the model observations. We need to satisfy the dynamic similitude first, and then we can discuss some uh, physical properties. So this is the first exercise. In the following class, there are around 5 to 6 exercises, and then we will see how to use the dynamic similitude for the problems we meet, and you will see for the different problem we will have the uh, different effect, and then we consider different uh, independent pi groups. So this is the exercise. The problem is the jack characteristics of the blimp, 5 meters in diameter and 60-meter long are to be studied in wind tunnels. If the speed of the blimp through steel air is 10 meters per second, and if a 1/10 scale models is to be tested, what airspeed in the wind tunnels is needed for dynamically similar conditions. So we assume the same air pressure and temperature for both model and prototype. So for these problems, the only pi groups left is appropriate is the real numbers. There are no compressibility effects, free surface effect, or gravity effects. So because our problem only meet the problem related to the viscous effect, related to the drag force. So the real number is defined by the rho VL divided the viscosity, and we need to satisfy and let the real number equals between the model and the prototype. And based on this dynamic similitude, we know that the rho m Vm Lm divided the mu m is equal to the rho G Vp Lp and the mu p. And we consider the problems is the incompressible fluid. So the rho is the same between the model and the prototype, and at the same temperatures and the pressures, so the viscosity also the same between the model and the prototype. So finally, we know that the Vn, the velocity in models, divided the Vp, the prototype velocities, equal to Lp divided Lm. And we actually know the prototype velocity is 10 meter per second. So how large of the flow velocity is in models? So it's equal to EP multiply the ratio between the length prototype and the models. Okay, so as we know, the VP is the 10 meter per second, and LP divided LM, which is uh, the information showing here, so it's equal to the 10. So finally, we know that the speed in the model should be equal to the 100 meter per second. So that will be the problems because we know that for the normal conditions, the airspeed need to less than 100 meter per second, and then we don't need to consider the Mach numbers. That's because the Mach number will smaller than 0.3 threshold. But in these questions, the exercise, our airspeed is around 100, so that's quite close the threshold for the airspeed. So it's usually we will have some trade-off. If we consider our problem need to satisfy the Reynolds number equals, and then we will meet some problem. The problem is the velocity model is too high, and then we need to further consider the dynamic similitude for the Mach numbers. And the slide just summarize if our problem always in the process conduit, and then in that way we know that uh, we don't have the free surface effect, so we don't need to consider the weight number. And then for this kind of problem, usually we assume the model conducted in the relatively low Mach numbers. So for the process conduit, usually the Reynolds number criterion is the most significant for dynamic similitude. So please keep in mind if your problem always focus on the closest conduit, and then you only need to consider the Reynolds number equals to satisfy the dynamic similitude. So for this problem is the prototype size is the 6 ft in diameters at the inlet, but the flow rate Q is required for the model if the prototype flow is the 700 CFS. In that conditions, we assume that the temperature for model and the prototype is the 60 degrees F, and that the model in that diameter is the 1 ft. So for these problems, usually we have some assumptions such as the no compressibility, so we don't need to consider the Mach number. And the second is the free surface effect, so we don't need to have the Weber numbers. And finally, this is a closest conduit system, so we feel there's no gravity effects, so we don't need to consider the flow numbers. So back to see the balance equation showing here, we only need to focus on the Reynolds number effects. So again, we just write down the Reynolds numbers in the model and uh, the Reynolds number in the prototype, and then make the balance. And finally, we only have the Vm divided by the Vp is equal to the Lp divided Lm. So the problem we meet, we need to require to answer how large the discharge in the model. So we just rewrite the equation. Balance is a Qn divided to Qp is equal to the Vnan and the Vpap. So we know that from the real number equals, so we can replace the velocity ratios by the length ratio here. And we actually know the ANP is equal to Ln squared and divided LP squared. So in that way, we can cancel out once the length. Okay, so we just cancel out, and then finally we know that the Qn divided Qp is equal to Ln divided by Lp. So the charge in models is equal to the Lp over Lm multiplied the Qp. So the exercise already show you the discharge in prototype is the 700 CFS. So and the ratio, actually we know that the model inlet diameter is 1 ft and the prototype is 6. So the ratio in here is 6 over 1 multiplied the 700 CFS. And then finally we will have the answer for the discharge in model is the 117 CFS. It's around to equal 3.3 CMS. So, but this charge is very large in the laboratory environment. So we would like to emphasize the idea that very few model studies are made complete satisfy the Reynolds numbers criterions. So this subject will be discussed further in the next sections. Okay, so this slide just summarize the ideas. Actually, the geometric and the dynamic similitude mean that the dependent pi groups are the same for both the model and the prototype. For these reasons, measurements made with the model can be applied directly to the prototype. So the equation 2 just remind you, please keep in mind, the left-hand side is the dependent pi groups and right-hand side is 4 independent pi groups. Okay, so this is another exercise. We're wondering to predict uh, the pressure difference. So as the equations, the exercise just explain the problems. A 1/10 scale models in here of the blimp is tested in wind tunnels under dynamic similar conditions again, and the speed of the blimp throws still air is 10 meter per second, the same airspeed velocities, and in that way we have a pressure difference 17.8 kilopascals is the measures between 2 points on the models. So the problem is what will be the pressure difference between the corresponding points on the prototype. So in the problems, we know that the temperature and the pressure in the wind tunnel is the same as the prototype. Because the temperature of the water in models and prototype is the same, so therefore kinematic viscosities for the model and prototype are equal. So in these problems, again, we go back to see we need to have the real numbers equals again between the model and the prototype. So again, we see that the velocity ratios between model and the prototype is equal to the diameter ratios LP divided Lm. and we know that's actually equal to n/1, and because the real numbers independent pi groups are equal, so that means for the dependent pi groups, such as the uh, pressure coefficients in for these systems shown here should be also equal to. So we know that we write down the balance for the pressure coefficients. So delta Pm divided the 2/1 rho m Pm squared is equal to delta P prototype and divided the 2/1 rho P dP squared. So we just make the balance and cancel out some constant values such as the density in here. So for this problem, we know that the pressure difference in models is equal to the square of the velocity ratio here and multiply the pressure difference in prototype. So the pressure difference in prototype, we actually know the value is the 17.8 kilopascal, and we know that the square of the velocity ratio is 100/1. So the answer for the pressure difference in model should be the 178 par. And then another problem, we don't require you answer the pressure difference. We change the problems we meet. Right now we are focused on and interested in the drag force from the wind tunnel testing. Or again, also the system is conducted by the 1/10 scale models. Okay, so in these systems, the drag force on model frames is measured to be the 1,530 newtons. So what the corresponding force could be expected on the prototype? So again, we just also make the real number balance, and we know that should be the equals, and we have the velocity ratios equal to the diameter ratios is in here is the 10/1s. But right now we change the dependent pi groups from the pressure coefficient to the force coefficients. But we know that the certain definitions for the force coefficients is the force divided the 2/1 rho v squared and the L squares. So only one difference in here is compared to the pressure coefficient is L squared. Parameters is related to the dimension of the area. So again, we just make the balance equations for the force coefficients, and then we just cancel out some constant values such as the densities in model and the prototype. So we cancel out the rho and we just again make the equation balance. So actually we know that the final formulas f the force in models is equal to the square of the velocity ratios and the square of the diameter ratios and multiply the prototype force. So if you replace the velocity ratios here by the diameters, so there will to be the LP divided the LM and the square and multiply the LM divided the LP squared. So notice that very interesting. Finally, they cancel out and finally equal to the ratio 1. So that means for these problems, we always have the result, the force in the model and the force in the prototype are always the same. So the slide just summarizes the idea by the sentence: when real numbers similitude is used, and the fluid properties are the same. So other condition we will have the fluid properties the same. Is usually we assume the pressure and the temperature conduct in the model and the prototype are the same, so we will have the same fluid properties. And in that way, the force on the models will always be the same as the force on the prototype. Okay, so so one thing difficult rising here is because the Reynolds number similitudes requires very expensive model testings because the usually we need to, the environment condition require the higher pressures or the large scale or using the different fluids. So the bottom centers just show one example. We have teach you on the previous slide is we satisfy the Reynolds numbers equals, and then we will have the too high airspeed velocities. In that way, uh, we have the two problems. The first one is we need to if the velocity too high, and then the compressibility effect will involve in our problems. And the second, if we need to create the relatively high airspeed in our testings, so the power requirement is also too high, and we will need to spend a lot of money to conduct this kind of the laboratory experiment. So too expensive, not always can be conducted. So so we just provided a possible solution to the problem we mentioned before. So it is possible to obtain all the needed information from the abbreviated test. Often Reynolds numbers effect either becomes insignificant as high Reynolds numbers or becomes independent of the Reynolds numbers. So the meanings. So I just put the figures and try to explain why we don't add the relatively high Reynolds numbers, and then we don't need to uh, to satisfy uh, the Reynolds number in that way. So but you see the y-axis is the force coefficients, the pressure coefficients, and the x-axis is the Reynolds numbers. And you see the pressure coefficients decrease when the Reynolds number increase. But at a certain threshold around here, even though you increase your Reynolds numbers, but the pressure coefficients are not sensitive to the Reynolds number changes. And this is the threshold around the 5,000 for the Reynolds numbers. Okay, so what are the advantage if we have this ability, characteristic and the properties showing the figures? So if we have the one problems and we see that the we know that the figures, the pressure coefficient is a function of the diameter ratios and the Reynolds numbers. So if the Reynolds number is large enough, the results are independent of the Reynolds numbers. So we know that the Cp, the pressure coefficient is only a function of the diameter ratios. So that's just two equations just highlight some ideas for the Reynolds numbers and the pressure coefficients. So the result of some model tests can be used to predict the prototype performance, even though the Reynolds numbers are not the same for the model and the prototype. This is especially valid for angular shaped bodies, such as model building tested in wind tunnels. And sometimes if because we would like usually we would like to have the dynamic similitude, and we will have the nano numbers equal and try to predict and the prototype performance for some dependent pi groups such as the pressure coefficient and the force coefficient and the shear force stress coefficients. But if we cannot satisfy the dynamic similitude, a possible solution we can just predict the prototype behavior by the computational fluid dynamic. We call that the CFD, which can use the numerical modeling to predict the prototype behavior based on some input model and the input parameters. So the slides showing here is another exercise. The prototype operates with the water at the 50-degree F and with a nominal reverse flow velocity of the 5 ft per second. The diameter of the prototype is 3 ft, and the tests are done in a 12/1 scale models facilities with the water at 60-degree F. So we actually know a head loss pressure drop of the 1 psid. The D here indicates the drop, usually related to the head loss for our systems measured with a velocity of the 20 ft per second. So what will be the head loss in the prototype, the actual nozzles? So we know that the condition for the prototype is the water at the temperature 50-degree F. So we have the density in here, and we have the kinematic viscosity is 1.41 multiplied 10 minus 5 powers. And the model, because we have different water temperatures, is the 60-degree F. And then we see that the density is the same, but a little bit difference for the kinematic viscosity, 22 the 1.22 multiplied 10 minus 5 powers. So we actually calculate the nano numbers for the model and the prototype individually. So we see actually very clear they are not the same for the nano numbers. Please notice that the nano number is high enough, it's over than larger than the certain threshold for the just the 5,000 we are writing here. So that means over this range of the nano numbers, the the, the pressure coefficient are not sensitive to the real number increase. So we can directly to say the back force the pressure coefficients are also equal for the model and the prototype. The test is valid. So again, when we go back to see our problem, we need to require answer the head loss in the actual nozzles. So we compute the pressure coefficient for the model first. We actually know the delta P provided in here is 1 psi, and we know that the velocities and we know that the low densities. So the pressure coefficient is equal to 0.37, and we know that the pressure coefficient in model should be the same as with the pressure coefficient in prototype. So, and then we actually know we can compute the velocity because we know that actually the answers the questions already tell us the flow velocity is the 5. So we know that the v is 5 and we have the density and this is the pressure coefficient in models. So we can predict the pressure drop indicate the heteros for the prototype conditions is 0.0625 psi. It's smaller than the pressure heteros in the models. So in some situations, viscous and the compressibility effects may both be important, but it is not possible to have the dynamic similitudes with both pi groups. Why? As we show one exercise, if you would like to satisfy the dynamic similitude for the neural numbers, and then you may have the relatively high speed. If the speed is high, and then you will meet some problem for the compressibility assumptions. So this is the problem again. So we have the 1/10 scale model of the automobile mobile is tested in a wind tunnel with air at atmosphere pressures and under the 20 degrees C. The automobile is the 4-meter long and travels at the velocity 100 kilometers per hour in air at the same conditions. So what should the wind tunnel speed be such that the measured drag can be related to the drag of the prototype? And we know that the experience show that the dependent pi groups are independent of the real numbers for values exceeding uh, the 10,000s. So this is quite higher than what we mentioned in the previous figures. Previously, we said that if the real number over than 5,000, and then the pressure coefficient are not sensitive to the real number increase. But the exercise showing here, we use more safety threshold is higher threshold. And we know that the speed of the sound is the 1,235 kilometer per hour. So we actually know of the model in the prototype under the atmosphere conditions with the temperature 20 degrees C. So we have a low for air is 1.2 and the kinematic viscosity is 1.51 multiplied 10 minus 5 power. So because of these problems, we first satisfy the nano numbers equal in model and the prototype, and then we have the velocity ratio is equal to 10. And we know that the model in prototype, so the velocity in prototype, so finally we know that the velocity speed required in the model is the 1,000 kilometer per hours. And if we compute the model number based on this velocity is equal to 0.81, which is larger than the threshold of 0.3. So actually the model number is too high for model test because it would be introduced unwanted compressibility effects. So you go back to consider we don't need to necessarily to satisfy the neural number balance because we know that the pressure coefficient will be not sensitive to the real number when the real number larger than uh, uh, 100,000 values. So we just replace. We know that we just consider assume our real number is directly equal to the 100,000 values, and then we compute how large velocity we need. And then so finally we only need to require are the 3.8 meter per second velocities in models, and then we can satisfy the Reynolds numbers of the dynamic similitude. So notice that there's a difference. We just convert the dimensional kilometers per hour to the meter per second. So another famous problem we meet usually is the free surface model studies the spillway models. If our problem is the spillways, and then the gravity effects are really important for these problems. So we need to use balances to satisfy the dynamic similitude for the fluid numbers. And we have the flow number. We know it's certainly divided by the velocity divided the root of the gravity multiplied the length unit. Usually the length unit here is related to the water depth. Okay, and at the high values of the Reynolds number, the relative viscous force are often independent of the Reynolds numbers. However, reduced scale model is made too small, then viscous force as well as the surface tension force would have a larger relative effect on the flow in the model than in the prototype. So this is the photo show the spillway behaviors, and another photo is a lateral view for the spillway modeling in the laboratory. So for this kind of the problem, we assume we conduct the 49/1 scale models, and of the proposed M is used to predict the prototype flow conditions. If the design fluid discharge over the spillway is the 15,000 meter cubic per second, what water flow rate should be established in the model to simulate this flow? So our unknown parameter is the Qm. So if the velocity we actually know is the 1.2 meter per second is measured at a point in the model. So, and what is the velocity at the corresponding point in the prototype? So we would like to answer the prototype velocity. So because the problem is for the spillway systems, so we first use the flow number balance, and the flow numbers should be equal between the model and the prototype. And so finally, we have actually know that the velocity models, the velocity in the models, and we know that the scale is the 49/1. So finally, we know that the VP velocity is equal to 8.4 meter per second in the prototype. And we need to have compute the discharge. So we also Qm divided the QP is equal to VNAM divided the VPAP. And then we just rearrange the both parameter and the change replace the velocity ratios by the length, and the area also change to the length dimensions. And then finally, we know that is the equal Qn is equal to Qp, and the length ratios of the 2/5 hours. So finally, we know that the discharge in models is around the 0.89 meter cubic per second. So, and this is the final case. We are focused on the ship model testings. The aim of the ship model testing is to determine the resistance that the system of the ship must overcomes. This resistance is the sum of the wave resistance. and the surface resistance. The wave resistance usually related to the problem of the gravity force, and the surface resistance is corresponding to the viscous effect. So the wave resistance is a free surface problem when we will have the liquid to gas interface involved in the systems. So first we need to consider the four numbers, and the second, the resistance of the surface is the viscosity effect, and then we can involve the real numbers. As I mentioned before, we cannot consider and satisfy the dynamic similitude at the same time for the four numbers, the real numbers. However, we usually we will satisfy the dynamic similitude for the four numbers. Because the wave resistance is the most difficult problem. So the model is operated according to the four numbers similitude, and then the wave resistance can be computed from the numerical modeling or the 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 analytic solutions. So this is the slide just summarize how can we deal with the shift model testing. So I would like to emphasize you need to consider the flow number first, and we can estimate and predict the wave resistance related to the viscous effect by remodeling or the directory computations. Okay, so this is the final slide. I just show the